Hi everyone, today we're going to discuss topic 7.9, Introduction to LeChatelier's Principle. So we've been speaking this entire unit so far about the concept of equilibrium and the fact that with equilibrium, the rate of the forward reaction is equal to the rate of the reverse. LeChatelier's principle is just a really interesting phenomenon that happens with systems at equilibrium. And so it's saying that if you have a system that's at equilibrium and it's disturbed by a change in temperature, pressure, or concentration, the equilibrium is going to shift so to counteract the effects of the disturbance. We'll discuss a little bit more about each of these and what this actually means, but let's say I have this reaction of A going to B, or any sort of reaction, and you can imagine it like I have two scales here, right? That these are on a little scale. What this is saying is if I push down on this, naturally this is going to go up, and so the system is going to change this side of the reaction to get everything back to normal. And so the reaction will change to reestablish equilibrium. So in the next few slides, I'm going to go through each of these scenarios, temperature, pressure, and concentration, and I'll show you how changing those will affect the equilibrium of a reaction. So first I want to make the case of just changing concentration in a reaction, and I'm going to use a sample reaction here. 3H2 plus N2 is in equilibrium with 2NH3. We can plot this on a graph of concentration versus time, which we've seen quite a bit, as follows. We'll have time on our x-axis, concentration on our y. And if we assume that these have already reached equilibrium, I'm going to label H2 as red, N2 as blue, and H3 as green, we might get a case such as this, right? We have the concentration of H2 here at equilibrium. We have the concentration of NH3, a little bit lower, and the concentration of N2 is here. And so we're at equilibrium, the concentration isn't changing as a factor of time, but now what I'm going to do is at this time right here, this dotted line, I'm going to add more H2. What will happen to the line of H2 is that it's immediately going to spike upwards. And like I said, because this wants to reach equilibrium, this reaction is going to shift in some way. Since I've added a whole bunch of this, what I'm going to do is I'm going to have to react some of this, and so my N2 will go down. And as a result, my NH3 will go up. And so I have this initial spike of H2, and because I want to continue to react and reestablish my equilibrium, it's slowly going to react until it reaches equilibrium again. Because I'm reacting, my N2 should be slightly decreasing as follows until it reaches equilibrium as well. And then finally, because I've reacted the H2 that I threw in there and I've reacted some N2, my NH3 should slightly increase as follows. And so now I've established this new equilibrium here, where at first I had my equilibrium initial concentrations. As soon as I added in something onto my left side of the reaction, my right side increases to compensate. And so if you add a reactant, the forward reaction goes faster. Conversely, if you add a product, the reverse reaction goes faster. So if you add something to one side, this essentially says that it pushes the reaction to go in the other direction. If I add H2, it's going to push the reaction forward, and I make NH3. Equally, if I added NH3, what you'll see is an initial spike of NH3, followed by reaction of NH3 to make more H2 and N2. Changes in volume and pressure also will have an effect on the equilibrium and have an effect on LeChatelier's principle. And this is because of the ideal gas law, PV equals nRT. Right? We got to remember that P is proportional to 1 over V, and V is proportional to 1 over P. And so if you change pressure, or if you change volume, you're going to be changing pressure. And so for this example here, where we have 2A goes to B, two different gases, if you change the volume, the equilibrium is going to shift based on how many moles are in each side. And so for this example in particular, if we decrease the volume goes down, that means the pressure will increase because the molecules are hitting the sides of the container with more force, so pressure should go up. The equilibrium is going to shift towards the products. The reason for this is because the products have fewer moles of gas. Right? We can see in our equation here, our reactants have 2 and our products have 1 mole of gas. And so if you decrease the volume but increase the pressure, this is going to want to form more product molecules in order to keep the volume and pressure back to where they originally were. Conversely, if we increase volume, this is going to decrease the pressure because now they're not hitting the molecules aren't hitting the sides of the container with as much force. What this essentially means is that you're going to favor reactants, or the side with more moles of gas. Right? You can see here, in this case, our reactants have more moles of gas. So if we increase the volume, we're going to favor the side that has more moles in order to get the pressure back to where it was, and so that there's more molecules hitting the side of the walls of the container. The important thing to remember is that if number of moles are equal on each side, in other words, if I have a reaction A goes to B and both of the coefficients are 1, then changing volume does not affect equilibrium. This is only for the case where you have different number of moles on each side. And so if we take the example that I showed before, 3H2 plus N2 is in equilibrium with NH3, and there's 2 of them. Right? If we look at the phases here, all of these are gases. So in our reactants, if we look at N total, for our reactant side, we have 4. 3 plus 1 is 4. For our products, we have 2. And so in this case, changing the volume will change the equilibrium. The third way we can use LeChatelier's principle is with changes in temperature. So let's take 2 different scenarios here. One is A plus heat reacts to make B. The other scenario is A forms B and it releases some amount of heat. If you go back to Unit 6, you would know that this is an endothermic reaction because you're adding heat to make the product, and this would be an exothermic reaction because you are forming heat at the end. In other words, delta H greater than 0 for the first, and delta H is less than 0 for the second. Well, if we think of changes in temperature here, we can realize that if we add heat or take away heat from a reaction, this can change the equilibrium. So in the case of endothermic, adding heat forms more products. And in the case of an exothermic reaction, adding heat forms more reactants. So depending on the type of reaction you have, if you heat it up or cool it down, you're going to push it one way or the other. One important thing to note here as well is that changing temperature is the only way to change K. or the equilibrium constant. And we'll get into this a lot more later, but the most important thing to know is that K depends on temperature. We don't have to worry about this too much yet, but we'll get into this more in the future. This is actually looking back to the demonstration that we did towards the start of this equilibrium unit. But here we have this endothermic reaction, delta H is greater than 0. We have cobalt hydrate plus 4-chlorine, and heat makes cobalt chloride and water. Right? This cobalt hydrate is pink, while cobalt chloride is blue. In this case, if we cooled down the solution, what we saw is that it turned pink. Essentially, it favored reactants because it's endothermic. But when you heated it up, as you add heat, this means the reaction is going to want to shift towards the products, and your products will increase as a result. And so what happens here is if you heat it up, it prefers the products. Another important thing to note here is that if you add some sort of inert gas, inert meaning does not react, and you keep the volume constant, then this has no effect on the equilibrium. And so let's take the same example we've been talking about, 3H2 gas plus N2 gas equilibrium with 2NH3. If I throw in, for example, helium gas, this does nothing because it doesn't react and it doesn't affect the equilibrium in some way. So just throwing in any sort of a gas isn't going to do anything. You need to throw in a gas that will actually perform the reaction. So let's look at this one example together very quickly. You have this reaction, which we actually just did in lab. Iron plus thiocyanate, SCN minus, forms iron thiocyanate, which is red. So you take two colorless solutions, you make a red one. So you add a colorless solution containing iron and thiocyanate ions. It forms the deep red complex, and then the net ionic equation, of course, is what is above. So it's asking you which of the following explains the observation when adding a few additional crystals of KSCN results in the red color becoming deeper, right? And so what we're doing is we're adding KSCN. In reality, right, when this dissolves, we're going to form K plus and SCN minus. And so all we're doing is just adding a bunch of this into the reaction. So we need to look at our choices here. It says adding the KSCN dissolves, which does happen, disturbing the charge balance in the solution, causing FeSCN3 to precipitate as a red solid. We look here in our description, it says nothing about precipitation, so this one really cannot be our answer because we're not seeing any sort of precipitation. All we see is that the color gets darker. In this one, it says the added KSCN dissolves, causing the solution to become saturated in SCN minus, which appear red at high concentrations. But if we look here, we've been told SCN is colorless, so this one can't be true either because SCN minus is not red. We look at C, it says adding KSCN dissolves. It causes the reaction system to respond by producing more product to partially consume SCN minus and reduce its concentration. What we see is that we have added this, and if we add something to this side, we essentially need to raise the other side in order to compensate because we want to reestablish equilibrium. And so C seems to make a lot of sense, but let's also read D. It says adding KSCN dissolves, causing the reaction system to respond by forming more Fe3 plus ions, which have a deep orange color at high concentrations. Based on what we know here, right, we know that Fe3 plus ions are colorless, and so this one also can't be true. But again, this would suggest that we're going towards reactants, which is not true. We got to remember, if you add reactants, the reaction shifts to make more products, and vice versa. You got to remember, if you add something to the left side, the reaction wants to go to the right. If you add something to the right side, the reaction wants to go to the left. And essentially, that is the rule with LeChatelier's principle. We'll do some more practice in class, but for now, that's all. Thanks, guys.